Okay, so welcome back. We are going to go over some Bernoulli's practice problems in this video. But first, we want to talk a little bit about some vocab with Bernoulli's because Bernoulli's can show up, the equation can look different depending on how you write it. And then based on how you write it, each of the parts of the equation have a different meaning. So there's quite a few little things we need to talk about. So first, we typically write Bernoulli's equation as pressure, and this is how we derived it, pressure divided by density plus v squared over 2 plus gz is equal to a constant, right? Or we can say that p1 over rho plus v1 squared over 2 plus z1 is equal to p2 over rho, right? If we can do 1 and 2, or we can just say it's equal to a constant, they mean the same thing. If we multiplied through by density on this equation, we would get, so if we multiplied through by density, we would get this equation down here. And here we have pressure plus 1/2 v squared plus rho gz is equal to a constant. If we then also multiplied by, we could also divide by a density. So if we divide by a density, by gravity, divide by gravity, we get a different equation, which is pressure over rho g plus 1/2 v squared over rho g plus z is equal to a constant. And in this equation, we introduce a vocab word called head, right? I have looked for why this was called, the word head was introduced here. And I haven't been able to figure out exactly where that came from historically, but each of these terms has a name. This one is called the, as you might expect, the pressure head. This one is called the velocity head. And this one is called the elevation head. And this was historically very useful because, as we talked about with manometers, pressures were typically measured using manometers. So you could then talk about all of these quantities just in terms of the heights you were measuring off of your manometers, right? So let's say you measured, you measured an elevation head of, or there was an elevation head of 18 centimeters, right? When you measure the pressure, then you might be able to just say, well, when I measure the pressure, I see that the pressure is 15 centimeters, so that I know the elevation head and the velocity head are X, and you can just subtract these things without multiplying by density and dividing by gravity and things like that, if you just keep everything in terms of height. Not so useful anymore, unless you deal with height a lot, like civil engineers deal with height a lot in terms of draining fluids and with dams and things like that, where you have large changes in elevation, and that's primarily what you're concerned with, right? Another way to do it is we take this equation again, where everything's in terms of pressure. In that case, we also have names for each of these parts. This is called the static pressure. This is called the dynamic pressure. Combined, these are called the stagnation pressure. And everything, all three terms, is called the total pressure. So let's talk about each of these in turn. So static pressure makes sense. This is the pressure you measure from a pressure sensor that you would put in the flow. Yeah, that's the pressure you measure from a pressure sensor you put in the flow. Dynamic pressure is not directly measurable, right? If you put a pressure sensor in there and there is dynamic pressure, it's not going to show up on your pressure sensor, right? We just call it the dynamic pressure. However, if we combine these two terms, and we then call them the stagnation pressure, because this is the pressure you would measure if the fluid stagnates, right? And the reason is because if the fluid comes to a rest, the energy from our kinetic energy goes into the pressure, right? It goes into the pressure energy, assuming there is no change in height, no significant change in height. Also, remember the implicit assumption that is always there when you're using Bernoullis, which is that it's an inviscid fluid. So there are ways to bring fluids to a rest where you convert a lot of that kinetic energy into thermal energy through losses, right? Viscous losses. You can imagine if you tried to flow the fluid through a sponge, right? All that small nooks and crannies are going to cause lots of viscous forces, which are going to reduce your energy without necessarily raising your pressure, because that energy then goes into heat, right? Which raises the temperature of your fluid. So, but the stagnation pressure is really useful because if the fluid stagnates in a way that it doesn't lose a lot of energy to viscous effects, then all this kinetic energy goes into your pressure energy, and you can measure this pressure energy. So we talked about a stagnation point earlier when we talked about the derivation for Bernoullis. We had a ball, and we talked about this middle streamline, which is right dead center in the ball. So it doesn't go up, it doesn't go down. The streamline is just above it, go over. Streamline is just below it, go under, right? And actually, this is three-dimensional. I would call it a cylinder, actually, so it's infinitely in and out of the page. That works. That makes it 2D. There's one on the backside, too, where you have a stagnation point where the fluid is completely stagnant, and then a streamline that leads away from it, right? It goes like this. So that's that. At that point, at that stagnation point, we get the static pressure, right? But the velocity is zero, and all of that kinetic energy went into our pressure. So we're now measuring all of at least these two parts of the energy of a fluid combined, right? And if we're clever about it and we measure the pressure, for example, here as well, we could then subtract the two and get some measure of the kinetic energy, which tells us the velocity of the fluid. So that's one way to measure velocities of fluids, which we'll talk about that later, again, like I said. So if a fluid stagnates, this dynamic pressure, like I said, is a we call it a pressure, but it's not a measurable pressure, right? Because it turns out that if you take an energy and divide it, make the energy per unit volume has the units of pressure, and it kind of shows up, behaves like a pressure does, sort of. This is obvious, right? We've seen this before. This is rho gz, rho gh, in other words, which is the hydrostatic pressure, right? Pressure due to the height within a fluid. Cool. All right, so let's get on to a practice problem. In this practice problem, my son has a bath toy that is basically a cup with a hole. And watching him play with it, I asked myself, how long does it take to drain the cup? And more importantly, how well does Bernoulli's model how long it takes to drain the cup? So if we ask this question, remember, a lot of times what engineers have to do is we have to take these ambiguous questions and convert them into more precise questions so we know which models to use to answer that question. So here, ask how long to drain. Well, drain means we're probably gonna have to worry about flow rates. If we're worrying about flow rates, remember, flow rate is a volume per time, Q. It's also equal to velocity times an area. If you look at the units of that, velocity is meters per second, area is meters squared, so we get a meters cubed per second. So that is a volume per second. So flow rates have implicitly a velocity in them, right? We also have a height. And if we have heights and velocities, we only have one model right now that will handle those, and that's Bernoulli's equation. So we're going to have to use Bernoulli's equation. So let's go ahead and break out our Bernoulli's equation and write it down. I'm going to use the model I'm most familiar with, or with the version of Bernoulli's I'm most familiar with, which is P over rho plus V squared over 2 plus GZ. The reason I like this version the most, put a 1 on those, because we're going to use a streamline and we're going to look at the top and bottom of that streamline. And this is P2 over rho, P2 over rho plus V2 squared over 2 plus GZ2. The reason I like this version of Bernoulli's is because the velocity is as simple as possible. And oftentimes if you're doing what I would call shenanigans or some kind of substitution or having to combine different models in order to remove variables. Because remember, most of what we're trying to do in fluids is just get down to one variable that we can solve for. That's how, and if we have multiple variables, we have to bring in more models and more equations and constraints to remove those variables. A lot of times it happens with the velocity. So if we keep it simple, then it's easier to do the algebra later. Okay, so we have this. Let's do our assumptions. Assume our density. Oh, sorry, let's assume actually gauge pressure first. Now you don't have to write this down, but it's a gesture of goodwill towards the graders, right? You're telling them, hey, I'm using gauge pressure. I know it's probably fairly obvious I'm using gauge pressure, but there's zero ambiguity here. Gauge pressure, B, density is equal to a constant. C, we're talking about steady flow here. And D, inviscid flow. And all of these assumptions are necessary in order to use Bernoulli's. And it's important we state these assumptions explicitly, because you and I know, or you will know by the time you're done with this section of the course, that you need, these assumptions are implicit whenever you use Bernoulli's. But somebody who's maybe not necessarily had a fluids course like this, like let's say you're working with a double E major or something like that, or like myself, if I wasn't teaching fluids, I can almost guarantee that when I took fluids almost 20 years ago, I knew this, but I wouldn't know it now, right? So people forget things, and it's important just to write them down so they can look at it and go, oh, wow, we're not using an inviscid fluid, and this isn't steady. So then they can ask you, like, how much does that affect the results? And then you can tell them some really smart answer and get promoted. So, okay, great. So this is our Bernoulli's equation. We're going to cancel out our pressures. Oh, we're going to cancel out our pressures once we do our streamline. Remember, you always do a streamline for Bernoulli's. So I'm going to choose to start my streamline on the surface of our fluid within our cup. And then I'm going to take my streamline down through the hole and then just out the exit of the hole. And the reason we're doing it just out the exit of the hole is because out there we have what is called a free stream. And a free stream has the pressure of the air that is around it, right? And since the air that around it is at atmospheric pressure, the beautiful thing we get to do is we get to make these zero. So both of these are zero because the top of our liquid is at atmospheric pressure and our stream of liquid leaving our cup is at atmospheric pressure. And so both of those are zero. And great, now actually, if you notice, density is now gone out of our equation, so we don't have to worry about the density of our fluid, which is wonderful. It's another reason to use this form of the equation. Later on, it would have canceled out later, but it's just, I feel like, happens more often and easily this way. Like I said, a little bit easier algebra. Okay, so we're also going to call point 2 here. Let's label our point 2 and our point 1. We're going to create a coordinate system where y and x are 0, our datum is at point 2, and that makes our z2 equal to 0. Great, and so Z1 is actually going to become our H. It's our variable in this case. That's as our cup drains, H will decrease, right? And our velocities are unknown. We have 2 unknowns in here, which means we have to bring in another equation, another constraint. In other words, another model in this case. So that other model we're going to bring into play is A1 V1 is equal to A2 V2, and we haven't talked about this a whole lot. This is essentially conservation of mass. We will talk about this in great depth later. There are some assumptions inherent in this model, but for right now, it's all you have to know is that these are like average velocities, right? Okay, so conservation of mass, we're going to take that and we're going to solve it for V2 because we want to plug this, we want to leave V1 in this equation, which we'll talk about why in a little bit. So we're going to say that V2 is equal to A1 over A2 times V2. Okay, great. So, oh, sorry, V1 times V1. Okay, started getting ahead of myself here. So 1 plus 3 into 4 gives us V1 squared over 2 plus GH2 times 2 is equal to A1 over A2 squared times V1 squared. So now what we're going to do is we're going to solve this for V1. We're going to take 2 steps to do it though. So 4 to 5 is V1 squared times, we're going to bring all the V1s together, A1 over A2 minus 1 squared. And that's going to be equal to G2GH, right? 2GH. And then 5 to 6 is going to result in, we're just going to take, divide and take the square root. We get V1 is equal to 2GH divided by A1 over A2 squared minus 1, all that square rooted. Excellent. Now, we need to be able to solve for when h is equal to 0, right? And technically, we still have 2 variables in here. We have h and we have V1. But V1 is just the height of the top surface of our liquid. And the top surface of our liquid is moving with changes when h changes. In fact, we can say that equation 7, that our V1 is equal to negative dH dt, right? Which makes total sense. The velocity is equal to the negative rate of change of that height of that interface. And what's negative is because we've been using velocity as if it had no sign. So a positive velocity down is actually a negative change in height, right? So that's why that negative is there. Great. So 7 to 8, or 7 plus 6 to 8. 8 gives us that negative dH dt. Oops, there we go. dH dt is equal to the square root of 2gh over a1 over a2 squared minus 1. We're going to take the negative sign over, and then we're going to separate and integrate. So 8 to 9 is going to give us dH over the square root of h is equal to the negative of 2g over a1 over a2 squared minus 1. All of that square rooted times dt. And if we're going to integrate, we might as well just do it. So let's draw our integrals. We're going to do limits on these. So we're going to do h naught, our initial height, to h. T naught, which is 0, so we're just going to leave 0 in there because you'll see it'll just drop out. If we do that integral, 9 to 10, we get that 2 square root of h minus 2 square root of h naught is equal to the negative of t times 2g over a1 over a2 squared minus 1. All that is square rooted, right? So if we cancel out these 2's, divide the t by 2, and solve for h, we get that 10 to 11. We get that h is equal to the square root of h naught minus t over 2 square root of g2 over a1 over a2 squared minus 1. All of it squared, right? And we could have actually solved for t and just solved for when h is equal to 0, right? That would have also worked. But this is a little bit more entertaining because we can plot h as a function of time. And that's exactly what I did over here on the right-hand side. So on the right-hand side, we start at a height of 43 centimeters, which is the depth of our container. And if I were you guys now, I would go and I would look at the video. I'm going to label it. I think it's going to be labeled whatever the number is for this video times 0.5. So I think it's going to be 13.5. yeah, it should be 13.5. So equation or video 13.5 in the fluid mechanics video list is going to be me doing this experiment where I drain the liquid from the container in my lab. And I don't time it in the lab because I'm going to let you guys time it using the video player in YouTube. So I want you to start it or check when it starts, check when it ends, and then come back. So watch that video, do that, and then come back having written down your answer for how long it takes, right? All right, I'm going to assume you paused it and are back now. So fun things about that video. One is that it's very easy to tell when the liquid starts flowing. It's quite difficult to learn when it stops flowing. And that's because one of the limitations for our model. Our model does not include surface tension, right? So at the end, when it starts dribbling, right, it goes drip, drip, drop, drop, and it's unclear exactly when it stops flowing is because the pressure effects due to surface tension. Because surface, you ever see when a droplet is kind of like held at the end of like a syringe or something like that, and the fluid's not flowing out, but the surface tension is holding the fluid up. Surface tension can produce pressures just like that, just like kinetic energy can, and changes in height. And that pressure is kind of counteracting the, almost counteracting the potential energy, the hydrostatic-ish pressure, but not quite. And so it's producing droplets until the surface tension is strong enough to just hold the liquid in place and prevent the thing from completely draining, right? But if you time it out, I got that it started at 48 seconds and ended at 59 seconds in the video, roughly, which gives us about 11 seconds for it to drain. And if we check the plot of H versus time, if we look, it comes down, and this actually mimics the video very well, right? It's going down very fast. You're like, oh my gosh, there's no way it's going to take 11 seconds. This is how I was feeling when I watched it the first time. I'm going to have to redo all my work. And then it starts slowing down, which is exactly what this plot says it's going to do, right? The velocity of our height is actually the derivative of this line. So the slope tells us what the velocity is. The slope is decreasing here. The velocity is decreasing. It's going very slow, and then it reaches an end. Actually, it turns out this is at 11.2 seconds, right? Which is almost remarkably good for what I got out of that video, right? Considering a couple things, right? It's this is not steady flow. Our height of our liquid in our system is not constant, right? So it's not steady flow. Our streamlines are not constant with time. This one looks like it might be, but actually the start moves downward with time, right? As time increases, the start of our streamline moves down. And a streamline, if we had drawn it off to the side, would look something like this, right? And then as time changed, it would continue to move down and end in the same spot, but it would change as well. So our streamlines are changing with time, which means it's not steady flow. It's also not an inviscid liquid. Water has a viscosity. So despite the fact that we weren't able to maintain those two assumptions, we still got a very good answer, right? Especially for the kind of experiment we did with the timing that we did, right? If we were in class, what I would do is I'd have all of you guys try to time it, and then we would average it to get a little bit better answer. But 11.2 seconds and 11 seconds on the video, which is not bad at all. Cool. All right. So we're going to do a quiz, not quiz, that talks about pitot tubes, which are used by airplanes to determine their airspeed. Remember, we talked about how you can use stagnation pressure to measure the velocity of an air. Well, we're going to talk about it exactly how airplanes do that, and calculate an equation that helps us determine the velocity from two different pressure measurements. Cool. For now, though, we're going to talk now about a practice problem where we look at the pressure variation across a wing, right? So estimating the streamlines and starting with one ending in stagnation point A. So remember, we talked about stagnation points on a wing. If we have liquid coming in from the left, we'll get a stagnation point right at A. And then we will also get a streamline that passes right over the top of our wing like this, right? And we'll get some on the bottom too, right? Go like this. Incidentally, you'll notice that after our wing, all of our streamlines are pointing down, right? The only thing that makes a wing generate lift is if the air moves down after it, right? Something has to go down for something to stay up. So if anyone ever asks you, they're like, wow, you're a mechanical engineer or aerospace engineer. Is it true that Bernoullis is what causes airplanes to stay in the air? No, it's not, right? Bernoullis just tells us the relationship between pressures and velocities along the wing. What makes a plane stay in the air is that air goes down, plane stays up. Okay, so starting with 1, ending in the stagnation point A, we have the pressure at A, the pressure at B, the pressure at C, and the pressure at D. Given these pressures, calculate the velocities at A, B, C, and D, right? All right, so our model, again, we're given pressures and we're asked to calculate velocities. It doesn't get more straightforward than that. We need to use Bernoulli's equation. So equation 1 is, in this case now, I'm going to write it in terms of pressures because we're given pressures, right? So we're going to have our static pressure, our dynamic pressure, and our pressure due to the height within a fluid. So we have P1 plus 1/2 rho V1 squared plus GZ1 times rho is equal to P2 plus 1/2 rho V1 squared plus GZ2, V2 squared, GZ2 times rho, right? So what's amazing about this is we're going to have to do a little bit of shenanigans here. Let's first write our assumptions that we need to use Bernoulli's, just to remind ourselves of them and also to make our grader's life easier. A, we're going to neglect our height. Now, think for a second why we can neglect our height. We have an airplane wing, right? So our hint is that it's in air, okay? And the reason then I would write next to the side right here is gas. It's a gas, so we're neglecting it, right? Again, remember you're trying to do active learning here. So when I pause like that and ask questions for you, and I'm trying to give you a little bit of time to write it down without having to necessarily pause the video every time. Okay, so other assumptions, go ahead and write down all of our assumptions that we need for Bernoulli's. There's 3 of them. B is inviscid flow. C, and I'm doing them kind of out of order from what I usually do, just because that actually helps with active learning, right? If you have habituated writing these things down in a certain order, changing the order actually engages your mind and causes you to remember them better, so that you're not just like in an exam freaking out and your habits leave you, right? You actually remember them. So rho is equal to a constant, and D, it's steady state, steady flow. Steady flow. Okay, so let's simplify our Bernoullis now based on our assumptions, right? We have a P1 and a P2. We have a V1 and a V2. We know these are velocities. We have we're neglecting our heights, which means we can actually say that these are equal to 0, which is great. And actually now we're going to draw a streamline. And this is where, again, remember we talked about how we're not necessarily using all of the assumptions in Bernoulli's in their purest form, right? And so Bernoulli says you have to follow, Bernoulli says you have to be on a single streamline, right? Well, what we're going to do is we're going to take a streamline, quote unquote streamline, starting at our stagnation point or right next to it. So maybe we're taking that streamline that's right next to the stagnation point. We're following it around to point B, point C, and point D, right? So we're going to have point 1 here at the top is our beginning, and we have 2, 3, and 4 here, right? So we can then simplify Bernoulli's a little bit. We can say that now that we know that our starting velocity V1 is going to be equal to 0 all the time, we can rewrite this 1 to 2 as if we simplify it, V2 is equal to P1 minus P2 over rho times 2, and all of that is going to be square rooted. Great, so now all we have to do is plug in P1 minus P2 divided by the density, it's air, so our density of our air is going to be essentially 1.2 kilograms per meter cubed, rho air. And we got our velocity, right? Cool, so go ahead and calculate the velocity at each point, A, B, C, and D, and tell me what you get. So again, I'm hoping you pause the video. For point 1, which is actually point A, right? A, we get that our velocity is equal to 0 meters per second, which makes total sense because PA minus PA is 0, which means our velocity is 0, right? There's no pressure difference. B, we get that because of that pressure difference, our velocity is 75 meters per second. And I'll let you guys do the rest of these again as an exercise to yourself. But only to state that we would expect our highest velocity to be at the top of a wing, okay? And then it will slow down after that till it comes back to our stagnation point. So B should be your highest velocity and C and D should be lower than that. Cool. So this is a well-functioning, streamlines for a well-functioning wing. Let's draw the streamlines for a stalled wing, right? So again, this is more practice identifying stagnation points than anything else. So go ahead and give it a shot. If you're familiar with it, if you're not, maybe go watch a few videos about wings stalling on YouTube. There are actually some really beautiful flow visualizations done on it. And I'm going to start drawing them now. So if you want to do it before I do, because you're trying to do some more active learning, go ahead and pause the video. But we got one stagnation point here. Now a stalled wing is really interesting, and we'll talk about exactly why this happens when we talk about wings. But the air doesn't have enough kinetic energy to make it all the way over the wing and comes to a stop. And when it comes to a stop, we produce another stagnation point. And so our streamlines now actually look like this. And the ones from below come up, and then we get a bunch of craziness that happens in here, which is all turbulent recirculating flow. The important part to remember, though, is that we have a stagnation point there. And what is a stagnation point? What is the pressure at a stagnation point, right? Is always the highest it's going to be anywhere in the fluid, as long as we can neglect height, right? Because all of our kinetic energy has gone into our pressure energy. So we have a high pressure here, which is kind of on the bottom of the wing. Normally we would have high pressure on the bottom of the wing and low pressure on the top of a wing, but now we have a stagnation point on top, which means we have high pressure here and here. And as a result, we lose the lift on the wing, right? And the physical representation of that is now, if we draw our streamlines far after our wing, we find that they're now traveling horizontally as opposed to going down like they are up here, right? Since they're traveling horizontally, we don't have any liquid going down, so our plane doesn't stay up. Cool. All right, so cool. So now we're going to look at flow measurement in pipes as our last example, I believe. Yeah, this is our last example. So we can use, obviously we talked about, well, we will talk about in class using Bernoullis to measure flow for an airplane. We could do something very similar for flow in pipes. We have to change the pipe to do it though, right? So one of the more common ways to do this is to use what's called an orifice meter. So there, when we put we have a round pipe, we put a ring inside of it that has a narrower hole through it. So the fluid has to go through a narrower hole. We know from conservation of mass, right? Let's write out conservation of mass, that V1A1 is equal to V2A2. So if we have a higher area here, a larger area here, and a smaller area here, let's do this with a different color. A smaller area here, we know that the velocity is going to be increased right inside of this orifice. And it turns out right after the orifice as well, right? Cool. So our question is after, if we're measuring the pressure at point 1 and point 2, because we have a differential pressure sensor that's measuring the pressure by having a tube that connects to the system here, but well before the orifice, and one right after the orifice. And can we estimate the velocity, which is really asking us, remember, we're always trying to convert these ambiguous questions into really concrete ones, is we are relating pressures, velocities, which model should we use, which should become fairly obvious. We're using a Bernoulli's model, right? So let's start writing out Bernoulli's, but before we do that, we're going to draw the streamlines for a fluid passing through an orifice, right? So if we're doing streamlines for fluid passing through an orifice, the important thing to know is that the fluid tends to follow nice, fairly well-behaved streamlines until it hits the orifice, and then it depends on the Reynolds number, so it depends on the velocity and the kind of fluid that you're putting through it. But afterwards, it will constrict and it will stay constricted and produce what are called, probably be turbulent afterwards, but it will produce these rotating low pressure regions here, which are roughly the same pressure as the fluid in this this high speed area here in the middle. So let's draw our other bounding kind of streamline here. And then you draw the ones in the middle. Try to do it before I do. Get another little bit of turbulence there. And then we've got the last one coming up. And a little bit of turbulence there, right? So you'll notice the streamlines narrow as they get through the orifice. When streamlines get closer together, the velocity increases. And then we have recirculating regions all around the orifice, just after the orifice, because the flow separates off the orifice. One of the things we'll mention a lot in this class is that fluids cannot take 90-degree angles, right? Unless they're going very slow. So if we have an orifice and it tries to go around each of these 90-degree angles, it's going to separate and it's going to produce a vortice. Cool. So the first thing we have to do is then, if we're going to use Bernoulli's, is we have to draw a streamline, right? So this is just like some of the forces equal to mass times acceleration. You always want to have a free body diagram that goes alongside it. If you're going to use Bernoulli's, you need a streamline, right? So our streamline is going to be from just outside here through the differential pressure sensor to just outside here, right? Now, the interesting thing about this is, again, we get to play a little bit fast and loose with what exactly a streamline is and what counts as a legit streamline. So in a tube, typically the pressure is the same all the way in the cross-sectional area of the tube, okay? So we're actually able to extend our streamline to the middle on both of these because the pressure is the same, roughly the same, the cross-sectional area of the tube. Even though the streamlines are actually moving horizontal and not vertically, right? Okay, the other thing which we will talk about, or in our problem for our quiz, not quiz, is that differential pressure sensors actually have a diaphragm inside of them that separates the fluids on either side. Now, there's not supposed to be fluid flow through this tube. The liquid in here is stagnant. And as a result, the fact that we have a thin metal diaphragm or thin plastic diaphragm doesn't actually affect the system, and we can basically draw a streamline that goes all the way through it. It's just really an example of how resilient the Bernoulli's model is towards breaking the assumptions that are used to derive it. Okay, so let's write out Bernoulli's. So we have, let's label our points here actually. Point 1 and 0.2. So let's write out Bernoulli's 1. Remember, we're relating pressures and velocities here. Since we're relating velocities and we're gonna have to do some shenanigans with velocities, I like to write out Bernoulli's as P1 over rho plus V1 squared over 2 plus G Z1 is equal to P2 over rho plus V2 squared over 2 plus G Z2, because eventually it'll just makes the algebra just a little bit easier. And we're going to assume, I don't know why I'm writing this in red. We're going to assume a couple things. We're going to assume the standard Bernoulli's assumptions. So go ahead and write those down before I do. Go ahead and pause the video and go look them up if you have to. But doing that is going to cause more learning than just listening to me and writing them down, right? So A, we're going to assume inviscid. B, we are assuming density is equal to a constant. And C, we are assuming steady flow. Now we're going to have to assume one final assumption, which I said earlier, which is that the P in pipe cross section is constant. Okay, and what that effect, so it is basically true, but again, these are the things you have to write down so that later people can know the kind of assumptions that you made and whether or not those assumptions are good enough for the accuracy they need, right? If you need this to be more accurate, then you're going to have to remove that assumption and find some other way to generate a model, right? Okay, so great. Let's look at this. We're measuring P1 minus P2. That's what a differential pressure sensor does. It measures the difference in pressure across it. So we know we're going to have to bring P1 and P2 together. So effectively, that removes one of them as a unknown. In fact, they're both known because we're measuring the differential pressure. We have no change in height, so we can actually cross out our z's, right? Make those equal to 0. We have no change in height. And all that's left is a difference in velocity, right? Okay, so let's write 1 to 2. 1 to 2. We have, let's bring our pressures together. P1 minus P2 over rho is equal to V2 squared over 2 plus V1 squared over 2. Awesome. So we still have two unknowns, V1 and V2, so we need another model. Turns out we have it right here. We'll call that equation 3. And now we're going to bring equation 3 to 4 is to solve that for V2, because we just want to know V1. We don't care what the velocity is in the orifice. We want to know what the velocity is in the pipe before the orifice, where it was like unmolested by that orifice, right? It's just the average velocity in the pipe. So V2 is equal to A1 over A2 V2, sorry, V1. Now we can combine equation 4 and equation 2 into equation 5. So 4 plus 2 into 5. And just a reminder, I number my equations because I think it's a little bit easier for you guys to follow. But I want you guys to practice this and have it become habit so that you do it on exams and you do it on homework. And it really makes the grader's job easier, and it'll help you get more partial credit. And also, hopefully, it gets you in the habit of making your work easy for others to follow. So P1 minus P2 over rho. We're going to bring the 2 from the two velocities over here to this side real quick. And we're going to set that equal to V1 squared times A1 over A2 squared minus V1 squared. This is going to be equal then to V1 squared times A1 over A2 squared minus 1, right? And then 5 to 6, to simplify it a little bit farther, 5 to 6, we're a little bit familiar with this now because we've done this problem earlier twice. Our V1 is going to be equal to the square root of 2 P1 minus P2 divided by rho times 1 over A1 over A2 squared minus 1. Okay. So provided we know these two areas and we can measure this difference in pressure here, and we know the density of our fluid, we can actually calculate the velocity of our fluid. And this is called an orifice pressure sensor. You can buy them. This is a cheaper version. What's important to know here is that this area is not actually as easy to solve for as you think it might, right? As the velocity in this fluid increases, the streamlines before the orifice stay roughly the same. They overshoot these corners more and more and more the higher the velocity gets, or the higher the Reynolds number gets. So at very high Reynolds numbers, you can get large overshoots. In fact, I think the area becomes about half of the orifice area. But at lower Reynolds numbers, that's not true. It becomes somewhere between the orifice area and half, right? And in terms of vocab, how you would say this is that A1 over A2 is equal to a function of the Reynolds number. And we haven't talked about this now, but this is the first time we're introducing it. The Reynolds number is equal to the density of the fluid times the velocity of the fluid, some characteristic velocity, some characteristic dimension divided by mu. In this case, the characteristic dimension would probably be the diameter of the orifice, right? And this is the viscosity, the dynamic viscosity of the liquid. Couple questions. Is this rotational or turbulent flow? Look at how I've drawn it and answer that question. All right, write down yes or no and why. Okay, so the answer to that is, yeah, it is totally rotational flow, and it is likely turbulent flow too. Most of the velocities that we're dealing with in these pipes that have an orifice plate in them are high enough to cause turbulence after it. Knowing that there's turbulence, right? Knowing what I told you about the overshoot, what are the sources of the error in this measurement system, right? Where does our model break down and how does it affect our result? So remember, we talked about conservative and non-conservative models. Here I want to know, what are the sources of error, and do they cause the velocity to be higher or lower than it actually is, right? So pause it, try to write down, try to think about it, I don't know, go for a walk if you need to let it stew in your head. But try to actually come up with an answer. Don't just write something down real quick and then listen, right? Think about all the things that break down in this situation and how they would affect our velocity, okay? All right, so sources of error in our system. One is we don't exactly know the area of our orifice plate. So when we plug that in here, we have an error in A1 over A2. Now I mentioned that this A1 over A2, the actual A1 over A2 is some fraction of the A1 over A2 of the orifice plate divided by the pipe, right? It can be as much as half and up to about 1, so almost the same, right? So if our A1 over A2 is smaller, right, then the bottom of our equation is going to be smaller, right? And our actual velocity is going to be higher than our measured velocity, right? So that is an error where our model undershoots or reality, okay? And where we don't know A1 over A2, our A1 or A2 being unknown, right? Another error is we talked about how this is both steady flow and inviscid, right? Well, we're clearly not steady flow if we have rotating vortices, and I draw turbulence as just kind of like crazy wild lines, right? So these if we don't have steady flow, and very much so if we have rotational flow, we're going to have to worry about viscous effects, right? When this flow rotates here, it just turns away and loses kinetic energy and turns it into heat. That's all it does. That's all these vortices do. And the vortices that are shed into the flow also do the same thing. So we're losing energy, right? We're losing energy, which means that the pressure difference we measure here is going to be smaller than it would be if we had an inviscid fluid. And if our pressure difference is smaller, if P1 minus P2 is smaller, then the V1 that we predict is going to be smaller than the actual velocity. So the fact that we have a viscous fluid is going to cause the model to undershoot reality, right? And cool. So we know now, right? Because we've done the hard work of thinking through this, we know that our model that tries to predict velocity from this orifice plate measurement of pressure is going to undershoot the actual velocity. So what can we do to mitigate this source of error? All right, why don't you think about this too? Think about all the labs you've done, things like that, which could help. Okay, so what we can do to mitigate these sources of errors is we can calibrate the device. In reality, that looks like a couple different things. One is I mentioned that A1 over A2, the actual, we'll call it A1 over A2 actual, not theoretical. The actual, or no, not actual is not a great word. We'll say effective. The effective A1 over A2, because remember, just to say it again, as we increase the Reynolds number, the water or liquid or oil or shampoo is going to overshoot this orifice plate and produce a narrower constriction, which means the area here, this cross-sectional area at our pressure measurement relative to the area back here, is going to change as a function of the velocity of the fluid. So in order to make this more accurate, we would say this is equal to a function of the Reynolds number, and we would measure this function. Right? And we would give that to whoever's using our plate. And that would do two things. One is it also takes care of our viscous fluid effects because the Reynolds number is equal to the ratio of inertial effects to viscous effects. And so it captures the amount of vortices in the flow, and we'll talk about this ad nauseum later. It captures the amount of vortices in the flow, and therefore roughly kind of captures the amount of energy lost to these. And so if you make this, if you find a function for the effective A1 over A2 and plug that in here, you can then create an implicit equation where you can solve this equation where your velocity shows up here. Because remember we said this is a function of the Reynolds number, so it's a function of rho V1 d over mu, right? And so by plugging V1 in both of these places and figuring out which V1 satisfies the equation, you can actually solve for the velocity. It becomes more complicated, but it's more accurate, right? And this is the ultimate trade-off that occurs in all models. The more complicated we make it, the more it costs us. It costs us more in time, or it costs us more in resources. So cool. All right, so that was our practice for Bernoullis. And I believe after this, we move on to, actually, I'm not sure what we move on to, but we move on to a different topic.